We're going to do our drill for the 2.8 choosing a good model. This whole section is going to be about choosing the correct regression model. So let's look at the drill. It says, using the data provided on the right, compute each of the following regression equations. Use years after 1790 as your independent variable. For example, 1790 would be 0, 1800 would be 10. So the first thing I'm going to do to make sure when I go to enter this data into my calculator is that 1790 I'm going to put in as 0 because that's my starting place. 1800 would be 10, 1810 would be 20, and I want to go through and I want to write these in because otherwise I will end up making a mistake and entering the wrong data, which I don't want to do. All right, so that's my first column, and I'm going to, just to remind myself, I'm going to highlight these values because these are the values that I want to put into my L1 column. And these values here, the population in millions, that's going to be what goes into my L2 column. And I've got some more data to do that same thing with over here. So I'm going to, that was supposed to be 100, sorry about that. This is 110, 120. I'm going to just keep going, and I'm going to do the same thing where I highlight. I do a lot of things like that because I am a very visual learner, and so I need things to be visually easy for me to understand. So I'm going to, again, I'm going to highlight in orange. These are going to be my L1, my independent values. This represents my years. And in yellow, I have my dependent, which is my population in millions. What I'm going to do now is I'm going to go over to my calculator and I'm going to enter this data. The orange values I'm going to enter in L1. The yellow values I'm going to enter in L2. All right, so I've entered the data in my calculator. And now I'm going to go to Stat and Calc, and I'm going to do the linear regression model first. And I'm going to do everything to 3 decimal places. So when I write down my line of best fit, it's going to be y equals 1.288 x minus 40.625. Notice that 5 is going to bump the 4 up to a 5. It also asks me to record my R-squared value. We always do the R-squared value to 2 decimal places, which would be 0.92. I am going to, for the linear regression model though, even though it doesn't ask for it, I'm also going to put the R, or correlation coefficient, which would be 0.96. That correlation coefficient, well, we're going to talk about the difference between the R, which is the correlation coefficient, and the R-squared, why I'm going to write down both in just a second. So let's go back to our paper, make sure we've recorded everything correctly. All right, so notice I've labeled both the R and the R-squared value, like I told you, and I put my line of best fit. It is always good to just note that our X value is our years since 1790, and our Y value is our population in millions. Okay. All right, so now in order to do my exponential regression model, I'm going to go back to my calculator. And I left off with linear regression, so I'm going to go back to Stat, and I'm going to calculate, and this time I'm going to go to exponential regression. And once again, I can go to 3 decimal places. So I'm going to get that y equals 6.033 times the b value, which is 1.020 to the x value. My r-squared value is 0.96. and my correlation coefficient, my R value, is 0.98. All right, so let's look at what we've written on our paper so far. All right, so I've written both of my equations, and I'm starting to compare my R-squareds and my correlation coefficients. I realize that as far as correlation coefficients go, the exponential regression model looks better, and therefore its R-squared value is also higher. So at this point, it looks like the exponential regression model is my best model at this point, based on both the correlation coefficients and the R-squared values. So now I need to go back to my calculator and calculate the quadratic regression model. So I'm here at exponential regression. I'll go to stat and calculate, and this time I'll go to quadratic regression, which is choice 5. Ask my calculator to calculate that. All right, and again to 3 decimal places. This time I'm going to get y equals 0.007 x squared plus, actually it's minus 0.114, so that 8 bumps the 3 to a 4, x, and then plus 6 point, that's actually going to become 0.110. That 109, in a sense, is going to get, the 6 is going to bump that up to 110. And my R-squared value is wow, it's almost 1. I don't want to say it's 1 unless the R-squared value is actually 1. I never want to write that down. So I'm actually going to write down the fact that it's 0.9989. And let's go back to our paper. All right, and so I wrote my R-squared value down as 0.9989. Because it wasn't a perfect 1, I'm going to have to take it out several decimal places. Otherwise, here, I guess I could have written 0.999. The 9 would have bumped the 8, but I felt like this was the best representation. So when I look at this, notice there's no correlation coefficient to compare to the quadratic. That's why we can't simply use correlation coefficients, which are the R values. We have to use R squared, because the only way to compare all 3 is to compare their R squared values. And when I look at that, the one with the highest R squared value is the quadratic model. So which model, based on just this information, I'm not looking at a graph. Maybe if I had a graph, I might pick a different one. Because they're all pretty good models from the way it looks. Which model is best? I'm going to say the quadratic, and why the R squared value is the closest to 1. And when I think about it, when I'm looking at population, I think that quadratic models many times fit population, because sometimes populations go up and down. They're not just always growing, because if populations never stopped growing and never had any times of decrease, then we would definitely be overpopulated. All right, I want to look at this page, because when we get to this section, and we're choosing a model and we're comparing, everybody starts to mix the different vocabulary up, especially R squared, and residuals. Everyone starts to think they are the same. R, which most of the times we denote with a lowercase r, but R, many times denoted just lowercase r, is the correlation coefficient. And that correlation coefficient is something that we use to determine what kind of a fit something is, and it's only for linear and exponential models. So only let's put a star here, only found with linear and exponential models. And that's because correlation coefficients can be positive or negative. Positive if it is an increasing relationship, negative if it's a decreasing relationship. So only found with linear and exponential, it's the correlation coefficient. Let's also say it can be positive or negative. I'll put that here. It can be positive or negative. So that is what R is. Now, R squared has no other name. This is called the correlation coefficient. R squared is simply called R squared. If you call R squared the correlation coefficient, you will lose points. You will have your explanation will be marked wrong, because that tells me you don't know what R squared is. R squared is simply R squared and can be used to compare linear, exponential, and quadratic models. Because all three of them have an R squared. They are literally taking the R value, the correlation coefficient, and squaring it. Therefore, because it's squared, it's always positive. R squared is always positive. It is not the correlation coefficient. The correlation coefficient is R. R squared is just R squared. And then residuals. Because residuals starts with the letter R, people think somehow R is a residual, or R squared is a residual. A residual is the error between the actual, also called observed value, and the predicted value. So residual equals observed minus predicted.